Hi, my name is Javier, and today I'm going to present you about our work on impartial selection with additive guarantees via iterated deletion, which is joint work with Felix Fischer, David Hannon, and Max Klimm. So let me quickly introduce the setting. So let's think of three agents, A, B, and C, who form a committee, and they want to select a speaker. So they vote for each other, and we represent votes by arcs. So we construct a directed graph. In this example, A votes for both B and C, and these two agents vote for each other. So the question is how we select a speaker, and the most naive mechanism we could think of is just select the top voted agent and break ties in some deterministic way, for example, alphabetically. And in this case, we would select agent B. But then what happens if agent C really wants to become the speaker, and she could think of removing her vote for agent B and then becoming the speaker herself? So then we see that the vote of C influences her own chance of being selected, and this is exactly the kind of situations we want to avoid in impartial selection. So the underlying assumption is somehow that agents are willing to reveal their true preferences as long as they are not affected negatively by this in their own chance of being selected. So more specifically, we look for mechanisms that are both impartial in the sense that the selection of each agent is independent of her votes, and competitive in the sense of selecting agents with many votes. So let me formalize this a little bit. So we consider a set Gn of directed graphs on n vertices and without loops, so we don't allow for self-votes. For example, the graph we considered before. And then a mechanism is simply a function that maps each such graph to a subset of its vertices of size at most 1. For example, a mechanism could just select agent B as before. And then we look for two properties. Impartiality formally would mean that whenever two graphs differ only in the outgoing edges of a single vertex V, then we either select vertex V in both of these graphs or in none of them. So for example, not selecting C in the graph on top would mean also not selecting her in the graph on the bottom, because this second graph is constructed just by deleting C's outgoing arcs. And finally, we measure the performance of a mechanism through additive approximation. So we say that a mechanism is alpha optimal if it always selects an agent with at least delta minus alpha votes, where delta is the maximum in degree on the graph, or equivalently the maximum number of votes that an agent receives. So with these definitions, we can take a look at the previous results in this setting. In terms of multiplicative guarantees, several works have been done. But as you already saw, today I'm focusing on additive guarantees. And here we can construct a small table with the bounds on alpha for impartial alpha optimal mechanisms. So just to be clear, we are focusing only on impartial mechanisms, and we're asking how good can we perform in these mechanisms. So a table of the results would look like this. We consider three different settings, namely the plurality setting, where we allow each agent to cast at most one vote. The second setting, we allow each agent to cast at most k votes, where we will assume k to be in the order of n to the gamma. And finally, the approval setting, we don't put a limit on the amount of votes each agent can cast. And here, the upper bounds represent mechanisms, because they're upper bounds in the additive deviation, and lower bounds represent impossibility results. So the first interesting result in this setting is due to Holzmann and Moulin in 2013. And they observed that for the plurality setting, since there are at most n arcs in the graph, there is at most one agent with floor of n over 2 plus 1 or more votes. And therefore, they proposed a simple algorithm that is select this agent in case it exists, and otherwise don't select any agent. And this is impartial because no agent can influence its own in degree, and it achieves an additive guarantee of floor of n over 2, because the worst case is that there is an agent with this amount of votes and the mechanism doesn't select it. For the other two settings, only the trivial bound of n minus 1 was there, and this comes from the trivial mechanism that never selects, and here the worst case is that an agent receives votes from all the other agents and is still not selected, so this gives a bound of n minus 1. And on the other hand, in terms of lower bounds, the bounded out degree setting, and in fact every setting admits a lower bound of 1, that comes from the fact that we cannot always select the top voted agent. And for the specific approval setting, Karagiannis et al. Proposed a couple of years ago a lower bound of 3, observing that for a specific counterexample on graphs of 4 vertices, this can be achieved. So now we can include our results in this table as well, because our work basically improves some of these bounds. And our first contribution is providing a mechanism that, for the case of sublinear out degree in n, it achieves an upper bound that is also sublinear in n, which is, for the case of out degree at most big O of n to the gamma, is big O of n to the 1 plus gamma over 2. And this specifically translates to big O of square root of n when gamma is equal to 0, meaning constant maximum out degree. And in particular, for the plurality setting, this means 8 square root of n. And for the case gamma equals 1, this just gives the trivial upper bound big O of n, also achieved by our trivial mechanism. But our second main contribution is showing that this is actually best possible by showing a lower bound of k for the case of out degree at most k, and specifically n-1 for the approval setting. And therefore, this last row of the table is now tight. So we finally slightly improved the lower bound of plurality from 1 to 3, but today I'd like to focus on these two bounds, which we consider to be the most important ones and are also more illustrative of the other bounds as well. So let me start giving an idea of the upper bound. This comes from a mechanism based on iterated deletion of outgoing arcs of the vertices from highest to lowest in degree. And we call our mechanism the twin threshold mechanism. You will see immediately why. And it works basically like this. We take as an input a graph and two thresholds, lower and uppercase t. And the mechanism just iteratively deletes the outgoing arcs of the vertices from highest to lowest in degree up to the lower threshold t. And then, of course, we have to break ties in some deterministic way in this step. And then it just asks whether there is a vertex above the upper threshold t. And if this is the case, it selects a vertex with highest in degree. Otherwise, it just doesn't select any vertex. So let me show you a simple example of this mechanism. So we consider a graph here with the vertices arranged from bottom to top according to their in degree and from left to right according to the tie-breaking order, for example, alphabetically or whichever order we like. So left vertices are preferred over rightmost vertices. And we distinguish two basic zones in such representation. Namely, the green zone is the zone where we do select in the end of the algorithm if some vertex is there. And the pink zone is the zone where we no longer delete outgoing arcs of the vertices. So the algorithm would basically look for the edge coming from a vertex topmost, leftmost. So it would be this arc in the first place, and the mechanism just deletes this arc, so the vertex that was pointed by this arc decreases one level. And then in this same level, we have still one arc, so the mechanism also deletes it. Then the next level, we don't have any outgoing arcs, so we decrease it to the next one, and this is the next arc from left to right, so the mechanism also deletes it. And finally, we delete these outgoing arcs. And here we don't longer delete arcs because the remaining arc comes from a vertex below the lower threshold t. And then we just ask whether there is a vertex above the upper threshold, and since this is the case, we select the vertex with highest in degree, which is exactly this one. So our result can be then phrased that as follows. This mechanism for graphs with out degree at most k, where k is big O of n to the gamma, is impartial and achieves an upper bound of big O of n to the 1 plus gamma over 2. And I would just like to give you a rough idea of why these two properties hold. First, for impartiality, the key lemma is the following. We show that if the mechanism wasn't impartial, then there would be at least one vertex in each level between the two thresholds. Yeah, with in degree or above, meaning with in degree at least j, for j between the lower and the upper threshold t. And the idea behind this is what follows. If the mechanism wasn't impartial, then there would be a vertex v star, which is selected for exactly one of two graphs, g1 and g2, and these two graphs only differ in the outgoing arcs of this vertex v star. But we show that for the outcome of this mechanism to differ in these two graphs, the only way is that there is another agent which ends up above the lower threshold t in one of these graphs and below in the other graph, so that its outgoing arcs are deleted only for one of these graphs. And this is the only thing which can make the outcome change. And then we show that for this to happen, meaning for the change in the outgoing arcs of V star to propagate to this vertex that changed from being above to below the lower threshold t, the only way is that there is one vertex in each level or above. Otherwise, this have no impact in the final level of this vertex below. I know this is just a rough idea, but if you believe it, then we have that the sum of the in degrees has to be at least the sum of j, from j equals the lower threshold t to the upper threshold t, which is this expression in the right. But on the other hand, we know that the in degrees sum up to at most k times n, because k is the maximum out degree in the graph, and this is big O of n to the 1 plus gamma because of how we define k. And then if we take values of the two thresholds such that the expression in the right is strictly greater than the expression in the left, we reach a contradiction, and therefore our initial hypothesis that impartiality didn't hold has to be false. And in fact, we can reach this choosing specific values of these thresholds in the order of n to the 1 plus gamma over 2, because in the right-hand side we have these thresholds to the power of 2. such that this expression is indeed greater than the expression in the left, and therefore we can guarantee to the mechanism to be impartial. And the final question is, how good is the guarantee given by this mechanism? And this comes from observing that the worst case scenario is that there is a vertex that is way above the upper threshold T, but because of deleting its incoming edges, it drops below the upper threshold T, and in the end it's not selected. And how far can this be? Okay, it's T minus 1 plus at most the number of vertices with deleting outgoing arcs. And this last number is at most K times N over T, because we only delete outgoing arcs from vertices above the lower threshold T, and there are at most K times N edges in total. And because of how we define the two thresholds and K, this is big O of N to the 1 plus gamma over 2 as our bound claims. So this concludes this sketch of proof for the general case, and then for the plurality case, it's just optimizing over the threshold so that we can obtain the 8 square root of N, but it's basically the same idea. Good. So let me now proceed with the idea of the lower bound. So recall that now we're in the setting of arbitrary out degree before we were evaluating bounded out degree. Now, if we have arbitrary out degree, our theorem said that we cannot perform better than n minus 1 in terms of additive deviation, which is equivalent to say that there's no impartial mechanism which is n minus 2 optima in the class of graphs with n vertices. So if there was such a mechanism, what would it look like? So n minus 2, like an additive deviation of n minus 2 would mean that for every graph where there is a vertex with in degree n minus 1, we select a vertex with in degree at least 1. So in this case, we have 3 vertices and some vertices with in degree 2, so we can only select vertices with in degree 1 or 2 in this kind of mechanism. So either A or B in this example. But we actually show, not this theorem, but a stronger result, which is the equivalent but for randomized mechanisms. Meaning that, okay, the slide is a bit messed up, but I will just keep going, which means that there is no impartial randomized mechanism P that maps instead of a graph to a subset of its vertices to a distribution over its vertices, such that the probability assigned to the vertices with strictly positive in degree sum up to 1 for every graph where we have in degree n minus 1 for some of these vertices. And this would mean, instead of the upper diagram, this would mean that we assign probabilities to each vertex, and this mechanism, if it existed, would assign probabilities to each vertex that sum up to 1 only for the vertices with strictly positive in degree. And why we look at randomized mechanisms is, in fact, in the drawing, is that we can assume symmetry without loss of generality. So just P1 for these two vertices, since they are symmetric. So we show that such mechanisms cannot exist in a specific class of graphs, which we call the class of graphs of ordered partitions. And I would just like to give you an idea of how these graphs look like. And these graphs are constructed as follows. We have some vertices, and then we partition the set of vertices, define an order over the partitions, and then add arcs from every vertex to the ones after it. So within the same partition and to within the same set in the partition and to the next sets in the partition. So from the first one to all the others, from the second to the third and the fourth, and from the third one to the fourth one. And now within each partition we have that the vertices are symmetric, so we can assign the same probability to all of these vertices. And the nice thing of these graphs, the first one, is that they always have maximum in degree n minus 1. So we can impose, if there existed a mechanism that, like the one we want to contradict, that the probability is assigned to the vertices with strictly positive in degree sum up to 1. And the second nice thing of these graphs is that if we take any set in this graph, and now we add outgoing arcs from a vertex in this set to all the vertices in the previous set in the partition, we also obtain another graph of ordered partition, and this is the unique other graph of ordered partitions with the same probability. And this looks like this for this vertex in red. So we add an arc to the previous vertex, and then we have one less set in the partition, but still the same probability assigned to this vertex and to the other vertex in the same set. And then the proof is just combining the equalities I showed you before about summing up the probability summing up to 1 over this class of graphs. And we exploit the combinatorial structure of these graphs, specifically scaling these equalities through, with some values which are equal to the number of isomorphic graphs to each of them, also known as the Fubini numbers in combinatorics, and then we can obtain a contradiction and therefore conclude that we cannot perform better than n minus 2. Good, so let me just wrap up. So in the first part of the talk, I showed how we provide a sublinear upper bound on the additive deviation for sublinear out degree in n, matching also the best known randomized upper bound for the plurality setting of big O of square root of n. And we basically, in the second part, show that when we don't bound the out degree of the vertices, then we can basically do nothing, because impartiality can force us to select a vertex with in degree 0, even if all the agents agree in one other agent. And of course, many questions remain open. First one is closing the gap for bounded out degree, of course, because we provide a sublinear upper bound, but the lower bound is still constant, so there is some gap there. Also in the randomized bounds, there is some gap as well. And finally, an interesting possibility is including weights in the votes and not just simple votes. And very little is known in this setting, and we consider it very important for practical applications. So that's the talk. Thank you very much for your attention, and I would be happy to receive questions. Yes.
So I want to make sure I've understood the algorithm first. This two-threshold method, can I see it as one that is providing impartiality by removing the votes of anyone likely to win? So you're above a certain threshold, and you're potentially a winner, and so we'll remove your votes and see if you stay there?
Yes, this is the basic idea, that among the set of winners, we would like to delete their impact in who is the winner, and therefore we remove the outgoing arcs. But we cannot do this for everyone, and we kind of filter the agents on who could become the winner and who could not. That's the basic idea.
The opposite of PageRank, rather than being someone who has a vote of confidence because they have a lot of votes in them, you're saying because they have a lot of votes in them, they're untrustworthy rather than trustworthy. First off, is this a fair election scheme? Like if you're deleting votes of people? And then second off, do you re-add the votes once you know that they're going to lose?
For the first question, maybe saying we don't consider an axiomatic approach to the problem, but rather a computer science approach in terms of minimizing the maximum deviation. So we're just looking at deviating the minimum possible from the maximum in degree, and therefore, if we define some maximum fairness, this wouldn't probably be fair in the sense of deleting it, just as you are saying, because it's clearly not fair to just say because you have too many votes, we are not counting your vote, but we're rather minimizing the deviation. So yeah, it's kind of a different objective. And could you repeat the second question, please?
So I guess this would also be related to fairness. So I guess it's irrelevant, but the idea was, would you re-add votes once you know?
Yes. Yes, no, in the mechanism we don't do it. No, we just delete them, and then we select the top voted agent after deleting the votes. Yes. No, thank you for the question.
The deviation you're allowing somebody to remove a vote, it seems like another deviation is they have to vote for somebody, but they can change their vote. That way. It seems like a sort of weaker set of deviations there. Would that change what you can achieve?
Sorry, I didn't get the question, sorry.
Seems like you're allowing an agent to not vote for anybody. And an alternative requirement is that you have to vote for somebody, but you don't want, so you can benefit by voting for somebody different. Would that allow you to potentially strengthen your results?
Yeah, I haven't think of, but yeah, the notion we're considering of impartiality is just that we don't allow any deviation to be profitable in the sense of having a higher chance of being selected.
I think the question was about abstentions, wasn't it? Whether you, if you force people to vote for someone. Yeah.
No, yeah, I didn't get it correctly then. No, we don't force people to vote for anyone. Abstentions are clearly possible, and this is also a possible deviation. Yeah. And for both the upper and the lower bound. Yeah, in case this is not a complete answer, we can, of course, chat offline. Yes?
I was just wondering if you've thought about this scenario where you force everybody to cast K votes, and if this may change, would it still be impartial, or would it maybe change the bounds as well?
Yeah, no. I mean, no, we didn't consider this in the setting, in the paper. But I mean, this is also an interesting setting, of course. Yeah.
What would happen if you allowed real votes, like for fractional votes? Like I take my one vote and I split it across, or is that already in all estimated systems?
No, I mean, this would be like the setting of weighted votes, kind of, right? The one I mentioned in the end, that's kind of open question. Yeah, this is very little understood, I would say. Yeah. Yeah, then, I mean, with weights, I mean, it depends if you allow like a fixed weight to assign a mass of 1 among different agents, or clearly if you don't bound the weight that you can assign to an agent, nothing is possible. But if you can only distribute a mass of 1, this is a very interesting question, I think, and it's very little understood. Yeah. Thank you.